Continuing to talk about linear systems, remember that a linear system looks like x prime equals ax plus by, y prime equals cx plus dy. Using our new matrix notation, you can take your x prime, y prime, put them in a vector. A, B, C, D is called your coefficient matrix times your vector x, y. And you can write it all out, or you can name your vectors and your matrices y and a and y prime. All right, so I've got this linear system, y prime equals 2, 3, 0, negative 4 times y. Let's just quickly write out what that is without any matrices or vectors. So first, y prime and y, those are bolded, so they are vectors. So that actually says x prime, y prime equals 2, 3, 0, negative 4. And that bold y is actually a vector with an x and a y in it. So now to translate this to a system, x prime equals y prime equals, we take our 2, 3 dot product with x, y, so that's 2x plus 3y. And then 0, negative 4 dot product with x, y, and you get negative 4y. So this is the system I'm dealing with. X prime is 2x plus 3y. Oh, y prime is negative 4y. All right, so I want to verify that these two vector-valued functions are solutions to the system. So vector-valued function just means that the output is a vector. Okay. So see how y1 is bold? That means that it's actually representing an x1, y1. So to translate, this says that x1, y1 equals e to the 2t and 0. Right? So here's one way, another way to say it, or here's another way to say it. I can take out the vectors. Oops, that's not x prime, it's x1. x1 is e to the 2t, y1 is 0. And then let's do the same translation for y2. So another way to say that would be that since y is bold, that's actually a vector, x1, y1, sorry, x2, y2 equals negative e to the negative 4t and 2e to the negative 4t. So this is x2 on top and y2 on the bottom. All right, so I'm asking you to verify that y1 and y2 are both solutions to the system, right? So the system's written up here. And I want to know, so I have to check two different solutions, and each one has two functions that I have to check in two equations. So there's a lot of checking that's about to happen. Okay. So let's do y1 first. So I'm going to just, how much space? I'll do it over here. Okay, so let's check y1. Okay. So I'm going to write down my system, x prime and y prime. X prime is 2x plus 3y. Y prime is negative 4y. And y1 was x1 is e to the 2t. Y1 is 0. Yeah, so we plug it in. So if x is e to the 2t, what's x prime? 2e to the 2t. So I'm going to put that in for x prime. 2e to the 2t. And then does that equal 2x plus 3y? So 2 times x1 is 2e to the 2t plus 3 times 0. Is that true? True equation? Yes. Check. All right, now I have to check the other equation, y prime. So if y is 0, what's y prime? 0 still, right? Derivative of 0 is 0. So y1 is 0. I'm plugging in its derivative here, 0 equals negative 4 times y, which is 0. Is that a true statement? Yes. Okay, so y1 is a solution. It satisfies both equations of the system.
So to kind of just point out what I did was I took x1 and plugged it into the x prime equation for x.
Yeah.
I got x prime.
Yeah.
It happened to work. That always worked that way.
How'd you?
So I took x1.
Yeah.
And plugged it in.
You put in.
Yeah.
Yeah.
That's how I found what x prime is on the left.
No.
Okay.
So
Work out that way.
because it was true in this case,
right.
Because it actually is a solution. You can't do that. So what you need to do is up here, like before you even start, you have to say, okay, that means that x1 prime is 2e to the 2t. And up here, that means y1 prime is 0. And then you have to plug those into the left sides. Make sure your equation is true. All right.
So you just plug your ones into your x.
I do need to check them both. I'm only checking y1 right now. Yeah, which is x1 and y1. Next, I'm going to do y2. So y2 was that x2 is negative e to the negative 4t, and y2 was 2e to the negative 4t. Before I start trying to plug into equations, let's take the derivatives, right? So x2 prime, what's the derivative of negative e to the negative 4t? 4e to the negative 4t. And then we'll take the derivative of y2, and that would be negative 8 e to the negative 4t. Now I'm going to plug into my two equations. So I know x prime is supposed to be 2x plus 3y, and y prime is supposed to be negative 4y. So in my x equation, in my x prime equation, I replace x prime with the derivative I took up here, 4e to the negative 4t. And I need to see, does that equal 2x plus 3y? 2 times x, which is negative e to the negative 4t, plus 3 times y, which is 2e to the negative 4t. Is that equation true? Yeah, because this is a negative 2e to the negative 4t. This is 6e to the negative 4t. Those end up being equal, yes. And then I went into my space for the other one. I'll do it over here. Y prime equals negative 4y. All right, so y prime is 8e to the negative 4t. Does that equal negative 4 times y, which is, yeah, thank you. 4 times y, which is 2e to the negative 4t. Is that statement true? Check. So both y1 and y2 are solutions to the system. All right, so I need to know y1 of 0 and y2 of 0. So y1 is bold. So that means they're asking me for the vector x1 of 0, y1 of 0. So go back up to my equation where I have x1, y1. If I plug 0 into both of those things for t, what is e to the 0? 1, so I get 1, 0. E to the 2 times 0, 0. All right, and then y2 of 0, we're looking for x2, y2, both evaluated at 0. So I'm going to look at my equations, x2 and y2, put in 0 for my t's, so I have negative e to the negative 4 times 0. And then my other one is 2e to the negative 4 times 0. So that's e to the 0 is 1, that's negative 1, and that's 2. All right, so then the rest of the question says, are those two vectors linearly independent? If you took linear algebra, you know what that means. And if you don't, I'm telling you in the next sentence. It says, the answer is yes, unless those two vectors lie on the same line through the origin. Another way of saying that is if one vector is a multiple of the other. Or is one of those vectors a multiple of the other? No, then they are linearly independent. All right, we have another solution to check, right? So there's a lot of checking going on in this section. Rather than finding solutions, we're just checking that things are solutions. All right, so I'm looking at a linear combination of y1 and y2. That means you just take a constant, put it on each one, and add them together. So y3, another function y3, is going to be 2y1 plus 3y2. It's called a linear combination of y1 and y2. So I need to first figure out what y3 is, right? So y3 is 2 times y1, and y1 was 2e to the 2t and 0. Or was it just e to the 2t? Hold on, I can't remember. It was just e to the 2t. I wrote the 2 twice. Yeah. Okay. E to the 2t and 0, that's y1, plus 3 times y2, which was negative e to the negative 4t, and 2e to the negative 4t. That's the y1 and y2 I gave you a little bit ago. So let's just simplify this, right? So this becomes 2e to the 2t minus 3e to the negative 4t and 6e to the negative 4t. So when you multiply a vector times a scalar, you just multiply every entry in the vector times the scalar. So this is 2e to the 2t, and this is 2 times 0. This is nope, because 2 times 0 is 0, right? Plus, and then 3 times 2 is 6. And then this is your x3, y3. So x3 is this new function, and y3 is this second entry. So now I got to check using that x3 and y3. So I have to check my equation was x prime equals 2x plus 3y. Let's check that one first. Okay, given that x3 is 2e to the 2t minus 3e to the negative 4t, what is the derivative of x3?
Over the 2 plus 12.
Good. So I just took the derivative of x3. That's my x prime. Okay. Now I'm going to see, does that equal 2x plus 3y? So 2 times x3, which is 2e to the 2t minus 3e to the negative 4t, plus 3 times y, which is 6e to the negative 4t. Is that a true statement? Simplify. We do end up with 4e to the 2t. When you distribute this 2, you get a 4e to the 2t, so that part works. And then you have negative 6 e to the negative 4t plus 18 e to the negative 4t, which is 12 e to the negative 4t. So you do that out, that works. So that equation's true. Then we just have to check the y prime equals negative 4y equation. For y, I'm using y3, 6e to the negative 4t. So on the left here, I'm going to put y prime, which would be negative 24 e to the negative 4t. And we want to make sure that equals negative 4 times y, which is 6e to the negative 4t. Is that a true statement? Yes. So we have another solution. I gave you two solutions, and it turned out that a linear combination of those two solutions was also a solution. Not a coincidence. Let's see, y3 of 0. So y3 is this. If I put 0 in for my t's here, I'm going to get 2 minus 3, which is negative 1, and 6 for my second entry, negative 1, 6. All right, so I used a computer program to make a direction field for this system that we've been working on. I want to sketch in the solution curves that correspond to y1, y2, and y3. In order to sketch in a solution curve, you need an initial value. You need a place to start drawing. And we calculated those along the way. So y1 of 0 was 1, 0. y2 of 0 was negative 1, 2. And y3 of 0 was negative 1, 6. All right, so y1 of 0 starts at 1, 0. So it starts right here. And if you follow the direction field from that point, the arrows just point directly to the right. So we've got this straight line solution, it's called. All right, y2 of 0 starts at negative 1, 2. And that happens to also lie on a straight line. It points right at the origin. It's hard to tell that, but it does. All right, and then y3 starts at negative 1, 6. Negative 1, 6 is like right here. And when you follow the direction field, it looks like that. So the solution curves y1 and y2 were very special solutions in the phase portrait. They're both straight lines. It's not typical of solutions to this system. There were only 2 straight line solutions on there, the 2 that we drew in. We're going to learn how to find those special solutions and exploit them to create a general solution in section 3.2. All right, so that was a demonstration of the linearity principle as discussed in 3.1 of your text. Here's what you can take away. The reading is a little bit confusing about the linearity principle, but there's like just a couple of key points. If y1 and y2 are 2 solutions, like choose the y1 and y2 I initially gave you, and k1 and k2 are constants, then any linear combination of y1 and y2 will also be a solution. So we showed one example where I picked k1 and k2 to be 2 and 3, and it worked. In fact, if you let k1 and k2 be arbitrary constants, like don't pick a 2 and a 3, but leave it k1 and k2, that's the general solution to the system, as long as y1 of 0 and y2 of 0 are linearly independent, which is why I had you check that. Geometrically, linearly independent means that the vectors don't lie on the same line through the origin. Algebraically, it means that one's not a multiple of the other. And when y1 of 0 and y2 of 0 are linearly independent vectors, we call y1 of t and y2 of t linearly independent solutions. So the linearity principle is important because it says that to find a general solution to the system, we just need to find 2 particular solutions, right? So You just have to often use lucky guess, sometimes a more sophisticated technique. But if you can find two particular solutions, you take a linear combination of them and you have all of the solutions, the whole general solution. So in the demo that we just did, I gave you the two particular solutions. In the class activities, you're going to use lucky guess to come up with two particular solutions. But don't worry, we have more sophisticated techniques than lucky guess that we'll develop in the rest of chapter 3.